Hello students and welcome back. So now we are going to talk about 4-bit comparator. So in this video we are going to talk about how can we comprehend the process of 4-bit comparison. We will see that what are the limitations using the conventional method of this system design. Then we'll design a 2-bit comparator and then finally a 4-bit comparator. So let us get started. So when I am given that you have to compare two numbers A and B, both of them are of the size 4 bits. If I have 4 bits of A and 4 bits of B, that means I have a total of 8 input variables. So in that case, I am going to have 2 raised to power 8, 256 input cases. That means we cannot have the truth table. So we must think of something else. So then how can we do that? We say, let us go back. When we were kids, we were asked to compare two numbers, right? And we were able to do that for decimal numbers very easily. We had a very simple logic. We used to observe the MSB. If the MSB of one number is greater than the MSB of other, we used to say number 1 is greater. Or if the MSB of number 1 is smaller than the MSB of number 2, then we say number 1 is smaller. If the MSBs were equal, the numbers are 98 and 97. MSBs are equal. Then we used to move to the next bit. And we kept on comparing like this. And eventually, if all the bits are same, then we used to say that these numbers are equal. So this is the simple process we had followed. So why don't we do that here as well? So first of all, let us implement a 2-bit comparator by using 1-bit comparators. So I have a 1-bit comparator here and one more. So these are two. I have number A which is having 2 bits, A1 and A0. I have second number B which is having 2 bits, B1 and B0. I am comparing the MSB, that means A1 with B1, and LSB A0 with B0. And each comparison operation is going to give me 3 possible outcomes. A0 is greater than B0, equal or less than. Same for A1 and B1, right? Now, how can I say that complete number A is equal to complete number B? For that, my logic is very simple. If A1 is equal to B1 and A0 is equal to B0. If these two cases are fine, I can say that number A is equal to number B. So I take one and I say if A1 equal to B1 and A0 equal to B0, then number A is equal to number B. So that is all good. Now, how can I say that number A is greater than number B? Well, in that case, first of all I look at the MSB. If A1 is greater than B1, I have a very simple decision. I can directly say A is greater than B. But if A1 and B1 are equal, then I have to look at A0, B0. So there are two conditions. The first one is if A1 is greater than B1, definitely A is greater than B. Or, and that is why I am having OR gate here. Or A1 is equal to B1 and A0 is greater than B0. If this condition matches, then also A is greater than B. Now you can start comprehending that if I have to design the circuit for A less than B, then what should I do? I say okay. Again there are going to be two conditions. The first one is if A1 is less than B1. If this is the case, I can simply say A is less than B. Or we say if A1 equal to B1 and A0 less than B0. So AND of A1 equal to B1 and A0 less than B0. In this case also A is less than B. So this is how we design a 2-bit comparator using two different 1-bit comparators. So now we can extend the same logic to design a 4-bit or any number of bit comparators. We'll need 4 1-bit comparators if we have to make 4-bit comparator, and the same process we will keep using AND OR gates, and we will be able to have the optimal solution. When it comes to the implementation, we can do it using the gate level or data flow modeling, and we can also do it very simply using logical operators, and we can use these 3 operators and design the circuit. So I'm leaving that to you. Design this comparator using any approach whichever you like. So students, that is where we end our combinational modules. We have a module test coming up, and then we will start talking about sequential circuits. Keep learning. Thank you.